Hi, today we're going to be looking at Newton's second law of motion in the real world. Today we are examining a ball rolling. We are assuming it has no net force acting upon it, so it theoretically should be moving at a constant velocity. This stems from Newton's first law stating that an object persists in constant motion or rest until acted upon. Since we assume no net force, then final velocity equals initial velocity. In this lab, we gather position data from Tracker, then use this data to create a model in GlowScript to predict the position of the ball. My first set of data wasn't completely accurate, so I went back and gathered position data from Tracker starting at a later frame and got more accurate results. Here is my original video, in the video with the position points plotted for data. I used these formulas to get my results. In this instance, I use average velocity because the velocity should be same over the entire time interval if we have constant velocity. So to find velocity for the ball, we can choose any 2 points from the position data. The position update equation below, the velocity is written in the code for the model. The computer iterates this formula over and over again until we reach the end of the time interval, and then we have a graph of position versus time. Here is where I found the velocities that I would input into my code. I use the first 2 data points to find velocity since it should be the same over the entire time interval. The slower velocity in the initial calculation is what led to the model underpredicting the actual motion of the ball in my initial analysis. The time values come from the camera. My phone shoots 60 frames per second and the 2 positions had 1 frame in between them, so the time change is 0.017 seconds. Here are the main places where I altered the code for my model. I had to input the velocity and starting positions to have the base for my model. I then had to input the net force as the 0 vector so that my velocity would stay constant in the last bit of code. The last bit is from the time loop where the computer is performing the calculations for the position. It updates the velocity from the last velocity and the position from the last position. Here is a comparison of my initial analysis with the model using the velocity calculated from that respective data. You can see the model underpredicts the motion of the ball. I think this is due to me starting the position analysis too early while the ball was still accelerating, before it got to its constant velocity. I think this has something to do with the highlighted change in velocity around 0.1 seconds. This is the reanalyzed data and the model based off the velocity calculated from it. This time the model overpredicts the position of the ball, which is more realistic result. I think this is a more accurate data set and model because I started gathering data when the ball came to speed. There are a couple important conclusions to draw from this. In actuality, there are net forces in real life, which is why the model overpredicts in the more accurate set of data. The model doesn't take into account forces like friction and air resistance. If it did, the model would be more realistic. This leads us to concluding that making assumptions in a computing model isn't 100% accurate, but we do know that making a model with a computer is a very powerful tool because I was able to get about 60 data points in only a second or two.